All right, so we're gonna get like a little bit of an intuition for arc length first. Don't obviously write all this down. I'll tell you when you need to write down a definition, but let's just develop sort of an intuition for how it works. So when we talk about length of a curve, you can think about, right, if we take some curve and we stretched it out straight and then we just measured it. All right. So if the curve is a polygon, we could find its length. So polygon meaning rigid sides, right? Straight line sides. And we would just measure the length of each side and then add them all together. That's easy enough. All right, so what about a smooth curve like a polynomial? And the process is going to be pretty similar to kind of the way we found volume or area, right? So when we found area, we would start with, right, here's my generic curve. We would start by dividing the interval into subintervals. And then we would create rectangles, and we could get like an estimate of that area by just adding up the areas of the rectangles, right? And then the way we could get better estimates is by dividing it into even more subintervals and using even more estimates. And the more subintervals, the better the estimate. And then we figured out, oh, we actually have this tool where we can create infinitely many subintervals, and that tool is the base of calculus, which is the limit, right? And we just let the limit of the number of subintervals approach infinity, and then we were able to evaluate that limit and thus find the exact area under a curve. Kind of the same idea here. We could find the length or the perimeter of this square pretty easily, right? We would just find the length of each side and add them up. Same for this hexagon. And notice that if we want to find the length of the circle, as we increase the number of sides of the polygon becomes a better and better approximation of the circle. This is like the basis of the book. Have we talked about flatland in this class? So it was a book written in like the 30s, and it was about, it's really interesting. It's about a society in a flatland. I'm trying to think of like the best way to say it. And it's like, okay, what if there was this society in a flatland, and he develops that the author does this whole world building where it's a hierarchy in the flat land, and like,
Dad, can we play a round of Among Us with you?
No.
Please.
Yeah, right. So Kaylin just direct messaged me. That's I'll tell you what he said, but that's the basis of it. But he does this world building where like there's a hierarchy, and it's dependent on the number of sides that you have. So a god would be a perfect circle, right? So soldiers who are like very low in the hierarchy are triangles, and then squares are like middle class, and then pentagons are like upper class, and so on and so forth. A high priest would be like a dodecagon or something like that. The more sides you have, the higher you are in this hierarchy. But it was written in the 30s, and some people say that it's like sexist because all women are line segments. But then it's also been argued like no, because women were also the most powerful, because since they were line segments, they could go invisible. So if this was a soldier, right, and his eye is here, in flatland, you have to think about this. If you exist in only two dimensions, you can't see what shape the others are, right? You can only see, like if you're a triangle and you're looking in this direction, and this is a square, you only see this side, right? Does that make sense? So you're only going to see that line. So the women were line segments, so they could be deadly because they could turn sideways like this and become invisible. And then they could kill people, they could pierce people. So I don't know, it was really interesting. But the way they got around that you could only see a line is that they said that there was like this fine, the author says there's like this fine mist in flatland, right? So if a triangle comes across, say, a pentagon, they would be able to tell it's a pentagon because since it's like a fog, they would see this side as darker and this side up here as lighter. So they could see like degrees of gradient, you know, and be able to tell that it's a pentagon versus a square or something like that. Anyways, it's a really interesting book. Not the world building's cool and the hierarchy is weird, but it talks about there's this 3 dimensions and a 3-dimensional being comes upon flatland and he's trying to, it's like a sphere and he's trying to explain to the flatlander what 3 dimensions is. And the flatlander has no idea, like cannot perceive of this. And the 3-dimensional being is like, look, I can see inside your body. I can see inside your houses. Here's what your house looks like. And it's like blowing the flatlander's mind because he can't see that. But if you're standing above them, like this is what their houses would look like. You could like see all their furniture in their houses and see what they were doing and stuff like that. You know what I mean? Anyways, and then there's another part where the Flatlander comes on across a 1-dimensional being where it's the line landers and the individuals on that are just points and they can't change. Anyways, I'm rambling. It's good. You should, Alex, has your dad read it or has he talked to you about it? Is that why you said that? One year I showed, there's a movie of it, but the movie it's like 4th graders made it. It's like, and they like gave up halfway through. It's so bad. The book is great though. It's really short. You should check it out if you ever come across it. All right. Anyways, so here's how we're gonna find arc length. I just realized I recorded all of that. So if you need to go back and you're like, oh, I forgot how to find arc length, you'll come across a 5-minute rambling discourse about flatland. Because I'm not editing that out. All right, so here's kind of the way we're going to deal with this, right? We're going to do the same thing that we did to find area, meaning we're going to start by breaking up the interval into subintervals, into some finite number of subintervals. And then we're going to find the y values of the curve at those subintervals, right? And what we can do is just connect those y values with straight lines. So that's going to give us line segments, okay? And all we want to do is be able to find the distance between those 2 points. So I want to find the distance between P0 and P1, P1 and P2, and so on and so forth, right? And we're going to denote that like this. So that's those 2 bars. It's not absolute value, it means magnitude. It's kind of a physics notation and it just means the linear distance between those 2 points, right? All right, and so the general idea, as you can see, I can start out just by finding the linear distance between these 2 points, but as I create more and more subintervals, you can see that the sum of those linear distances will better approximate the length of the curve, right? As I use more and more subintervals, I get a better and better approximation of the curve itself, which is what I want. Okay. With that in mind, here's kind of your first definition. We'll define the length L of curve C that has equation y equals f of x on the interval from a to b as the limit of the lengths of the distances between pi minus 1 and pi. So it's the sum of all the distances, all the linear distances on the subintervals, but we're going to let the number of subintervals approach infinity, okay? All right. I'm going to pause here. Go ahead. Is basically we need to come up with a formula in terms of x for finding the distance between two arbitrary points. All right. Well, let's see if we can develop this just on a separate page so that I don't overwhelm you. So I'm going to say the distance between, actually, let me do this first. I'll kind of draw out what I'm talking about. So what we're looking at is some arbitrary curve. We have some subinterval. We'll call this P sub I minus 1, and this is P sub I, right? And what we want to find is the distance between P sub I minus 1 and P sub I. And so the way you can think about this is that they're both going to have They're both going to have coordinates, right? So this is going to have coordinate x sub I minus 1 and y sub I minus 1. And this is going to have coordinates x sub I and that'll be y sub I, right? All right, so do you guys remember this thing called the distance formula? It's basically an application of the Pythagorean theorem, right? And so the distance formula is just the square root of y2 minus y1 squared plus x2 minus x1 squared. Well, in this case, it's going to be yi minus y sub I minus 1 squared plus xi minus x sub I minus 1 squared.
I'm hungry.
All right, well, in math, we call the difference between two y values, another name for that, isn't that just delta y?
I don't know where my...
So I'm going to call this delta yi squared
I'm hungry, Dad. I'm gonna get the cookie. And I'll get my iPad.
plus delta x squared. So hold on. Sorry, that's a good question. So the reason we notate it delta yi instead of delta y, delta x is created by us. It's a consistent, it's the same across the entire interval, but delta y may be different depending on where we are in the curve, right? It depends on the function itself. So it's just to differentiate that all the delta y's won't necessarily be the same, right? So if I have a curve like that varies wildly, then I would divide up the delta x's evenly, right? But like on this interval, that delta y is going to be different than, say, on this interval, this tiny delta y. Does that make sense? So it's just to indicate that the delta y's will be different depending on what interval we're looking at. All right. So we're going to go back. I'm going to remind us of this thing called the mean value theorem for derivatives. And the mean value theorem for derivatives basically says that there exists some x, I'm going to call it xi star, on the interval between xi minus 1 and xi, such that the derivative at that point is equal to the slope between the endpoints. And all that says, if you remember, all that's saying, it's been a while since we've talked about it, is that say that that's our curve. It's just saying there's some point, let's call it xi star, such that the slope at that point matches the slope between the endpoints, right? And that's true for any smooth curve. So any differentiable curve. And I can manipulate that formula by multiplying. All I'm going to do is multiply over the denominator. So that's going to say that f of xi star times xi minus 1 equals f of xi minus f of xi minus 1. And I know I reversed the order. The order doesn't matter as long as it's consistent. So hold on. Just to not be confusing. All right. So why that's useful for us is that really what this is saying, remember that this is just delta x, right? So what I'm saying is that delta x times f of xi star equals, and that's just delta yi. When I did what? Oh, I'm sorry. I just left out the prime. You're right, Catalin. Thank you. I'm sorry. There's a lot going on. Jill's rollerblading around me, spilling snacks. The dog's eating them. Okay, so the whole reason that this is useful is because we have this distance formula up here that we were developing, but we need to get it only in terms of x, right? And so now I can replace that delta yi with this. So I can say that delta yi is just, this whole thing equals the square root of f prime of xi times delta x squared plus delta x squared. All right, and then we can simplify. So notice that I have a delta x squared in both terms, so I'm going to factor that out, and I'm going to go, all right, I have delta x squared times, so I would have f prime of xi star squared plus 1. And then since this delta x squared is under the square root, I can just take it out of the square root as delta x. So this becomes the square root of f prime of xi star squared plus 1 times delta x. Remember what this is. This is just the distance between any two arbitrary points, the linear distance between any two arbitrary points on the curve, right?
I need some water. All this
Okay. So remember how we found the exact area, whoops, the exact area, or sorry, the exact rather length of the curve was this. We took the sum of all of the individual linear distances of our subintervals, right? So this definition, based on what we just came up with, is now going to become the limit as n approaches infinity of the sum from I equals 1 to n of, and now I'm just going to replace this kind of description of the distance between any two points with our expression in terms of x, which was the square root of f prime of xi star squared plus 1 delta x, right? So this is the limit way of writing it, but we now, once we're going to use infinitely many subintervals, we actually have a better notation for that, and that's integral notation, right? An integral is just an infinite sum. So I can replace that piece with an integral, and I'll just denote that my interval is from a to b. So once we use infinitely many intervals, the x-axis is no longer indexed, right? It just becomes a continuous x, a continuous variable x. So that just becomes f prime of x squared plus 1. And once we use infinitely many intervals as well, what does delta x become? You guys remember delta x becomes infinitely thin, and what do we call it in integral notation? Just dx, the differential dx. And now we've developed a formula for finding the arc length of a curve over an interval. Let me give you a cleaner version of this. There you go. So we want to find the length of the arc of the semi-cubical parabola given by the equation y squared equals x cubed between the points 1, 1 and 4, 8. So you can notice that these points are on the top branch of this thing called a semi-cubical parabola. So we can isolate y by taking the square root, and we can just focus on the positive square root because it's on the top branch, right?
Yeah.
And the other thing I can do is just recognize that the square root of x cubed is the same thing as x to the 3 halves. That'll be a little easier for us to do calculus with, right? All right, and so our arc length formula is the length equals the integral from a to b of root f prime of x squared plus 1
I'm okay.
dx. Jillian, sit up now, or you're going to time out.
Okay.
All right. So let's set this up. Length is the integral. And in this case, a and b are x coordinates because we're integrating with respect to x. So it's these x coordinates. So it's going to be 1 and 4. So I'm going to do integral from 1 to 4 of root 1 plus. Now we need to find the derivative of this. So if y is x to the 3 halves, f prime is going to be 3 halves x to the 1 half, right? And then we want to square that. So f prime of x squared is 9/4 x. Does that make sense? All right, so it's going to be 1 plus 9/4 x dx. All right, we need to evaluate that. You guys just took an exam over evaluating integrals. What technique would you use to evaluate this one? Not everybody at once. Don't overthink it. So this one I noticed that there's only an x underneath the square root, so I should just be able to u sub this. So if I just let u equal what's under there, then du is 9/4 dx, which is just a constant multiple, so I can just move that to be over with the du, right? So 4/9 du is dx. So then my integral just becomes 4/9 integral root u du. And since this is definite, I can just go ahead and update my limits of integration, and I don't have to go back to terms of x. All right, so when x is 1, u would be 1 plus 9/4, which would be 4/4 plus 9/4. So u would be 13/4. And when x is 4, u would be 1 plus 9, so 10. There we go. I have an equivalent integral. I can just go ahead and evaluate that as is. So 4/9 integral u to the 1 half du from 13/4 to 10. So what's that going to be? 2/3 u to the 3 halves from 13/4 to 10.
Oh, what a beautiful butterfly.
All right, plugging in those limits of integration, you can do that in your calculator, but this is all going to come out, if we leave it exact, as 1/27 times 80 root 10 minus 13 root 3. Okay, well, we can also do this with functions that are functions of y. So if x is a function of y instead, all I have to do is interchange the role of x and y, and I end up with the integral from c to d of 1 plus g prime of y squared dy. So note that now you're integrating with respect to y. So those are y coordinates. Your limits of integration are y coordinates. With respect to a different variable. It's not a huge deal. So we're going to talk about the arc length function. And so, hold on. So for the arclength function, all I'm going to do, I'm going to change my variable of integration to t, and I'm going to rewrite this as s of x equals the integral from a to x of root 1 plus f prime of t squared dt. And so notice that my variable is x, t is just a dummy variable, but this is giving me the ability to create a formula to find the length from A to any other point on the curve. All right, so we're going to find the arc length function for the curve y equals x squared minus 1/8 natural log x, taking the point p0 at 1, 1 as the starting point. So in this case, I'm going to be looking at the integral from 1 to x root 1 plus f prime of t squared dt. All right, so if f of t is my function, and I think of that as just t squared minus 1/8 ln t, then the first thing I want to do is find f prime, right? Which would just be 2t minus 1/8 times 1 over t. Okay, and then I want to square that. So that's going to give me 4t squared. Let's see. Minus 1/2 plus 1 over 64. T squared, right? And then I want to add 1 to that. So if I do 1 plus that, notice that all that's going to do is I'm going to add 1 to the negative 1/2. That's going to make it positive 1/2, right? So it's just going to be 4t squared plus 1/2 plus 1 over 64t squared. Which is kind of good news for us, because when it was minus 1/2, notice that it factored down to a perfect binomial square, to 2t minus 1 over 8t squared. Now that it's plus 1/2, this will still factor down to a perfect square. It'll just instead factor to 2t plus 1 over 8t squared. And you could verify that by multiplying it out. And the reason that's good news is because, remember, we're going to have to plug all that into this integral. So it becomes the integral from 1 to x of the square root of that, which is 2t plus 1 over 64t squared, quantity squared, dt. So that's really good for us, because now we have a perfect square under a square root. We can just take the square root. We don't have to do anything crazy like use a trig substitution or anything like that. We end up with just 2t plus 1 over 64. I'm going to rewrite that as t to the negative 2, because we are going to be doing a little bit of calculus with it, right? We're going to do some antiderivatives. All right, but now we have a an integrand that we can deal with pretty trivially, right? So it's take the antiderivative. Antiderivative of 2t will just be t squared. Antiderivative of 1 over 8t to the negative 2. If I add 1, it's going to be minus 1 over 8t to the negative 1. And I'm going to be evaluating that from 1 to x. All right, so plugging in x, I get x squared minus 1/8 x to the negative 1. And then plugging in 1, I'm going to have minus 1 minus an 1/8. All right, so final answer, x squared minus 1 over 8x minus 7 over 8.
Mommy, I can eat a seed. I can't eat a seed because it's gone.
Yes, you're right. All right, I need to go back. I'm sorry, guys. There's a lot going on here. I gotta go back a few steps because you're right. Here it should just be 1 over 8t, and I got distracted.
I'll get that. What?
Okay. That changes a lot, though, right?
18.
Normally, my daughter is doing this with my wife, but my wife had a doctor's appointment, so
Hey,
it's kind of chaotic. All right, so let's think of this as 1 over 8 times 1 over
I
t.
can't.
And let me do it right this time. T squared plus 1/8 natural log t from 1 to x.
Sorry, Mom.
X squared plus 1/8 natural log x, and then it would be minus 1. And then when I plug in 1, natural log of 1 is just 0, so that's it. There's our final answer. So what this is it's a formula, right? It's a function
18.
where I could plug in any x value, and it will output the length between this point 1, 1 and that x value on the curve. So let's just real quick, let me pull up Desmos and we can kind of look at that. Hopefully get a visual of it. So
I have to get my skeleton. I just want my skeleton.
So if we look at x squared minus ln x, and then the point 1, 1. All right, so any value that we plug in, so if I plugged in like 2, that would be that point, right? And it would give us, if I plug in 2 to my formula, it's going to give us the distance along that curve between those 2 points. So, for example, s of 2 would be 4 plus 1/8 natural log 2 minus 1, which is 3 plus 1/8 natural log 2. About 3.09. And that's just the distance, like I said, between those 2 points along that curve.